Stop what you're doing right now. If you're using Spring Security in your application, there is a good chance you're sitting on a ticking time bomb. Let me tell you about a company. They were a fintech startup processing millions in transactions daily. They thought their Spring Security setup was bulletproof. After all, they followed the tutorials, they used geo tokens, they had authentication and authorization in place. One Tuesday morning, they got a call from their cloud provider. Someone had downloaded their entire production database, including 50,000 customer credit card details. The attacker found an exposed Spring Boot Actuator endpoint that was leaking AWS credentials. They didn't even need to hack the application. They just need to read the credentials from Actuator environment endpoint. The cost, it's 10 million in damages, regulatory fines and lost customer trust. All because of a simple configuration mistake that I'm going to show you how to fix today. In this video, we are going to cover 10 critical Spring security mistakes that I have personally found in production applications. These aren't theoretical vulnerabilities. These are actively being exploited by hackers right now. We are going to look at real vulnerable code, understand exactly how hackers exploit it, and I will give you the secure code you can copy paste into your applications today. Let me make sure you don't become the next headline. So, mistake number one, it is disabling CSRF protection because you are building REST APIs. I see this all the time. Developers read somewhere that REST APIs are stateless, so CSRF doesn't apply, and they just disable it. This is dangerous advice. Here is what actually happens. CSRF or cross site request forgery works because your browser automatically sends cookies with every request to a domain. If a user is logged in into your banking application and visits a malicious website, that website can make a request to your API and the browser will automatically attach the session cookie. Without CSRF protection, your API can't tell the difference between a legitimate user request and a malicious request from another website. Look at this vulnerable code. I have seen this exact configuration in at least 5 production applications. The developer disabled CSRF with that one line .csrf.disable. Now here is the attack. A user logs in into their banking application. They got a session cookie. Then they visit a completely different website, maybe a news site with malicious ads. That ad contains JavaScript that automatically submits a form to the banking API post request API transfer with attacker's account number and a large amount. The browser sends the request with the user's session cookie. The bank's API sees a valid, authenticated request and transfers the money. The user never clicked anything. They just had the bad luck of visiting a compromised website. Let me show you the fix. Instead of disabling CSRF entirely, we enable it with a cookie based token repository. This allows JavaScript clients to read the CSRF token from the cookie and send it in the XSRF token header. Now, malicious websites can't make requests because they don't have the CSRF token. Mistake number two, exposing Spring Boot Actuator endpoints to the internet. This is a big one. Spring Boot Actuator provides endpoints for monitoring and managing your application. Things like health checks, metrics, and even heap dumps. In older versions of Spring Boot, these were exposed by default. Even in newer versions, developers often manually enable all endpoints for debugging and forget to disable them in production. Let me show you how dangerous this is. When you set management.endpoints.web.exposure to .include to star, you are exposing endpoints like slash actuator slash heap dump. This downloads a complete snapshot of your JVM memory. This contains everything. User sessions, database passwords, AWS credentials, JOT tokens, all in plain text. Second endpoint is slash actuator slash environment, env. This shows all environmental variables. If you have database URLs, API keys, or secrets in environmental variables, they are visible here. The next endpoint slash actuator slash gateway slash routes. If you're using Spring Cloud Gateway, this can be exploited for a server-side request forgery attacks, allowing attackers to access internal services. Here is a real exploit I found documentation in the Wiz security blog. An attacker simply downloads the heap dump with a curl command and then using this string commands to extract the text from the binary heap dumps, like your AWS access keys or JWT tokens. In one case, this led to a complete AWS account takeover because the application had IAM credentials in the memory. The fix is simple but critical. First, never expose all the endpoints. Only expose safe ones like health, info, and metrics. Second, disable dangerous endpoints like env and heap dump entirely. Third, move the actuator base path to something less predictable like slash admin slash actuator. And most importantly, add Spring Security authentication so only admins can access these endpoints. Mistake number 3, hard coded JOT secrets in your code. This one makes me want to cry. I can't tell you how many times I have found JOT secrets directly in the application or properties or hard coded in Java classes. If your JOT secret is in your source code, anyone with access to that code can forge authentication tokens for any user, including admins. Here is a real scenario I found on GitHub. A developer had committed their JOT secret as a constant string, my super secret key 12345. This was in a public repository. This means anyone could clone the repo, extract the secret, and generate valid JOT tokens. How does the attack work? The attacker simply takes your hard-coded secret and uses it to sign a JOT token with whatever claims they want. They can set the subject to admin, add a role claim for role admin, sign it with your secret, and your application will accept it as valid. The worst part, even if you remove the secret from the current version of the code, it's still in your Git history. Anyone can browse previous commits and find it. There are even automated tools that can scan GitHub for these patterns. The secure approach is to never hardcode secrets. Use environmental variables or better yet, a proper secret management systems like HashiCorp Vault or AWS Secrets Manager. Your code should read the secret from the environment at runtime, not have it baked in. Also, when configuring your JOT decoder, always specify the expected signature algorithm. This prevents algorithm substitution attacks where an attacker sends a token with algorithm none and your application accepts it. Mistake number 4, CORS wildcard misconfiguration. CORS, which is cross origin resource sharing, is a browser security feature that prevents websites from making requests to different domains. But when developers run into CORS errors during development, they often just set allow all origins to make error go away and then forget to fix it in production. This is a critical mistake. When you set access control allow origin to star and access control allow credentials to true, you are essentially telling the browser allow any website to read responses from my API using the user's authenticator session. Here is how the attack works. An attacker creates a malicious website at evil.com. A user who is logged into your application visits this site. The malicious site contains JavaScript that makes a fetch request to your API. If your code's policy allows the origin and credentials, the browser will actually send the request with the user's sessions cookies and your API will respond with the sensitive data. The malicious JavaScript can then read that response and exfiltrate the user's personal information. This is different from CSRF because with coarse misconfiguration, the attacker can read the response. With CSRF, they can only trigger actions but not see the result. The fix is to never use wildcards. Explicitly list your trusted origins. In production, this should be your exact domain names. No wildcards, no regular expressions that can be bypassed. Also, only allow the specific HTTP methods and headers that your application actually needs. Mistake number 5, the BCrypt password length bug. This is a recently discovered vulnerability that affects BCrypt password encoder in Spring Security versions 5.7.0 through 6.4.3, and it's a nasty one. Here is the problem. BCrypt has a maximum input length of 72 bytes. Any character beyond the 72th byte are silently truncated. But the CVE 2025 vulnerability is even worse. BCrypt password encoder.matches will incorrectly return true for passwords longer than 72 characters as long as the first 72 characters are the same. What does this mean in practice? Imagine two users have the passwords that start with the same 72 characters but have different endings. When they try to log in, the password validation might incorrectly accept the wrong password. Let me show you the vulnerable scenario. User 1 has a long password ending with 123 and user 2 has a similar password ending with 456. If the first 72 characters are identical, Bcrypt might match both passwords against the same hash. This is critical authentication bypass. This vulnerability was given a CVSS score of 7.4, high severity. The Spring Security team has released patches, but you need to upgrade to the fixed version 6.3.8 or 6.4.4 for open source users. But there is also a code level fix you should implement. Always validate password length before encoding or matching. Check that the password is between 1 and 72 characters. This prevents the truncation issue entirely. Even better, consider migrating to Argon 2, which is now the recommended password hashing algorithm. Spring Security 5.8 Plus includes Argon 2 password encoder with sensible defaults. Argon 2 doesn't have this length limitation and is more resistant to GPU based cracking attacks. Mistake number 6, leaving permit all in production. This is probably the most common and most embarrassing security mistake I see. During development, we often disable security to make testing easier. We add dot request matches, API star star permit all, so we don't have to authenticate while testing endpoints. The problem is with the deadline pressure and the complexity of deployments, this temporary configuration often makes it to production. And when it does, your entire API is exposed to the internet without any authentication. Here is a real security audit finding I encountered. A production API had permit all on all the API pattern. When I made a simple GET request to API users, I got back a complete list of all users, including their password hashes, social security numbers, and salary information. No authentication required. No API key, just a simple HTTP request. The fix is to use Spring Boot profiles to have different security configurations for development and production. In development, you can have a more relaxed configuration. In production, every endpoint should have explicit authorization rules. Better yet, don't use permit all as a shortcut during the development. Instead, create a test user with known credentials and use for those for testing. This way, your security configuration remains consistent across environments. And always do a security review of your security configuration before production deployment. Look for any permit all patterns that shouldn't be there. Mistake number 7, SQL injection in Spring applications. You might be thinking, SQL injection, that's a solved problem, right? We use JP and prepared statement, but you would be surprised how often I find SQL injection vulnerabilities in Spring Boot applications, even ones that claim to be secure. The most common pattern I see is developer using JDBC template but still concatenating strings to build SQL queries. Let me show you a real vulnerable example I found in production application. The developer had a method that allowed sorting search results. They concatenated the sort column and sort order directly into the SQL string. The problem is that you can't use prepared statement placeholders for column names or sort order. They had to be part of the SQL string itself. An attacker can exploit this by sending a malicious sort by parameter like 1 and semicolon, drop table user semicolon. When this gets concatenated into the SQL, it becomes select star from users order by 1 semicolon, drop table users, semicolon, and then ascending. The database executes the first select, then executes the drop table command, and your users table is gone. This is a classic SQL injection attack. Another common pattern in building in clauses by concatenating a string of IDs. If the ID's parameter comes from user input and looks like 1, 2, 3 and the bracket or 1 equal to 1, the query becomes select star from users where ID in 1 to 3 or 1 equal to 1. The or 1 equal to 1 makes the condition always true, returning all users instead of just the specific ones. The secure approach is to always use parameterized queries with placeholders. For JDBC template, use question mark placeholders and pass the values as parameters. For dynamic in clauses, use named parameter JDBC template with colon IDs placeholder and pass a list. For dynamic sorting, where you can't use placeholders, implement a whitelist. Only allow specific column names that you know are safe. Never concatenate user input directly into SQL strings. Mistake number 8. Insecure Remember Me cookies. The Remember Me feature is convenient for users. They don't have to log in every time they visit your site. But if implemented incorrectly, it creates a persistent authentication vulnerability. Here is how the standard Spring Security Remember Me cookie works. It contains the username, an expiration timestamp, and an MDF hash of those values plus the user's password and a security key. The default expiration is 2 weeks. The problem is that if the cookie is stolen, maybe from a public computer or through XSS or from browser storage, the attacker can use it to authenticate as the user until it expires. Even if the user changes their password, the cookie remains valid because it's already been issued. This is particularly dangerous because cookies are often not treated with the same security consciousness as passwords. The secure approach is to use persistent tokens stored in the databases. With JDBC token repository implementation, each Remember Me token is stored in a database table with a series ID and a token value. When a user uses Remember Me, the token is validated against the database. If the token is stolen, you can delete it from the database, immediately invalidating it. Also, reduce the token validity from 2 weeks to something shorter, like 1 day. This limits the window of opportunity for attackers. And use a strong randomly generated key from a secure vault, not a hard coded string. Mistake number 9, Method Security Annotations Bypass. Recent CEVs have highlighted vulnerabilities in how Spring Security handles method level security annotations. CVE 2025-41248 and 22223 reveal that under certain conditions, security annotations on methods can be bypassed, leading to authorization failures. But there is a common issue that isn't even a CVE. It's a design pattern that developers often got wrong. That's self-invocation of secure methods. Here is the problem. Spring Security uses proxies to intercept method calls and enforce security annotations. But when a method within the same class calls another method, it bypasses the proxy. This means if you have a public method that calls a private method with @pre-authorize, the security check is skipped. Let me show you the vulnerable pattern. A public update user method calls a private update user method that has the pre-authorize annotation. Because this is an internal call within the same class, the proxy doesn't intercept it, and the authorization check is never performed. Solution is to move the secured method to a separate bean or a component. When you auto-wire that component and call the method, the proxy intercepts the call and enforces the security annotation. Also, be aware of the recent CVEs. Spring Security 6.3.8 and 6.4.4 include fixes for these annotations bypass vulnerabilities. Make sure you are on the latest versions to get these security patches. Mistake number 10. Session fixation vulnerabilities. Session fixation is an attack where an attacker tricks a user into authenticating with a session ID that attacker already knows. This allows the attacker to hijack the user's session after they log in. Here is how the attack works. First, the attacker visits the application and gets a session ID, let's say ABC123. Then the attacker crafts a phishing email with a link that includes this session ID. When the victim clicks the link and logs in, they use the same session ID. The attacker now knows the authenticated session ID and can access the victim's account. Spring Security has a built-in protection against this, but you need to enable it. The fix is to use session fixation migration. This changes the session ID when the user authenticates, so the session ID the attacker knew became invalid. Also, configure additional session security settings. Limit the number of concurrent sessions per user. Set session timeouts and ensure cookies are HTTP only and secure. These settings make session hijacking much more difficult. So before we wrap up, here is a comprehensive security checklist you should review before every production deployment. Go through each of these items and check them off. If you are disabling CSRF, make sure you have a proper justification. Check that your actuator endpoints are restricted and not exposing sensitive information. Verify that job secrets are in environmental variables, not in your code. Make sure course origins are explicitly listed with no wildcards. Review all permit all configurations to ensure they are only on truly public endpoints. Check that all SQL queries use parameterized statements. Validate password length before BCrypt encoding. Ensure remember me tokens are stored in databases. Also, check your CVE patch status. Make sure you are on Spring Security 6.3.8 or 6.4.4 to get the fixes for the BCrypt and authorization bypass vulnerabilities we discussed. Use security tools like OSAP dependency, check to scan your dependency, SonarQube for static code analysis, and OWASP Zap for dynamic testing. These tools can catch vulnerabilities before they reach production. We now have the knowledge to build secure Spring Boot applications. Remember, security is a journey, not a destination. You need to stay updated on new vulnerabilities and best practices. If you found this video helpful, hit that like button and subscribe for weekly Java security tips. Leave a comment below which of these mistakes have you seen in production. I would love to hear your stories. Thanks for watching.